So I will try to take a step back and explore how we could get food system transformation towards sustainability. Well, we have big challenges, and the first one is how could we end hunger? This is the target of the Sustainable Development Goal 2, SDG 2. However, as explained during my pitch on the first day of this conference, we have to understand how this could also connect with other challenges like health, like water, like biodiversity, climate. So it's really a nexus of problems we have to solve by changing the global food system. And this relates, in fact, to the 17 SDGs. So it's really a major undertaking. This was the vision of this Food System Summit organized by the United Nations in 2021. We will have a stocktake of the summit in August. And there are 5 specific objectives here. Ensuring access to safe and nutritious food for all, shifting to sustainable consumption patterns, boosting nature-positive production at sufficient scale, advancing the equitable livelihoods and their value distribution, and building resilience to vulnerabilities, shocks, and stress. So you see how, let's say, the global community framed those 5 challenges. It's quite interesting to see. Let me now explore with you what is this landscape of problems we are having with the global food systems. I will just take a few examples. The first one is really that we are losing a lot of food. We have to realize that the food system includes the production, processing, distribution, consumption of food, and the output of these activities with their implications for socioeconomic, environmental dimensions at the global scale. So we are losing a lot of food, and we are also with very large problems with malnutrition. Malnutrition is often called a triple burden because it includes undernutrition. So we have around 820 million people worldwide that are chronically undernourished. Micronutrient deficiencies, that's about 1.2 billion people, like not having enough zinc, enough iron, or enough vitamins. And we have an epidemic of overweight and obesity, which is actually leading to a very large burden in terms of chronic diseases. So right now, this is a leading cause, malnutrition, of illness, disability, and mortality. 1 in 3 suffers, and it will be higher in 2030. It's estimated 1 in 2. So we have a huge problem there. I address this issue of food losses and waste, but it also contributes to around 10% of the anthropogenic greenhouse gas emissions. So if we were to reduce this, and let me say that the losses are mainly in the low-income countries where you have problems with the logistics, with the conservation of the commodities, and the waste, they are mostly in the high-income countries where we tend to overconsume and waste quite a lot of our food. So we could certainly address this, and this would have huge benefits for the environment also. Then we need to consider this malnutrition issue. So it's not only tackling the food access, which is a key issue for undernourishment. It doesn't, in fact, require a lot more food to be produced. It's really an access problem in our days. But it is also rebalancing our diets with more fruits, vegetables, so more fibers for your microbiota, more protein crops and nuts. And this would come with actually rebalancing the production systems, going towards integrated systems, diversified crop rotations, increased genetic diversity, and the resilient and low-emission livestock systems. This would certainly support climate change adaptation and mitigation. So if we have this perspective where, in fact, we need to transform our food system to have healthy and sustainable diets, we realize we can do a lot. Because, for instance, if we reduce in the high-income countries the consumption of meat, the consumption of milk, because it is, in fact, a bit excessive compared to the nutritional recommendations, we could certainly have more land for ecosystems or for bioenergy, and this would, in fact, release millions of kilometers square of land with scope benefits for environment and health. So let me now introduce the vast risk we have with climate change. this is really a risk to food supply stability. This is a well-known graph from IPCC, which is the burning ember graph. So you see those colors going to the purple when you have increased warming. So far, we are very close to, unfortunately, the 1.5 degrees Celsius target for warming. We're already at 1.2 degrees Celsius. We are really at risk of exceeding 1.5. And already we see infrequent price spikes that affect individual countries. So indeed, climate change with droughts, with heat waves, is reducing the access to food and creating price spikes already. If we move towards 2 degrees Celsius and more, then we will have regional shocks because there are multiple bread baskets that are in fact interconnected through climate and may be affected, and this may really rise the price for entire regions. And if we move beyond that to 3 or 4 degrees Celsius, we are really at risk of having our global food supply disturbed. So you understand this is a major risk. I referred to also the micronutrient deficiencies. Well, that's a bad news because increased atmospheric CO2 actually leads to further reductions in the micronutrients in grains, and this means this will aggravate the nutrient deficiencies. We have some problems with economic models to capture all this because they often rely on general equilibrium as an assumption, which is not what we observe. They capture a rather modest increase in food prices, but what we observe is that, in fact, when we have heat and drought, we have conflicts, we have migrations, and this aggravates the food security issue. And we know certainly that the most vulnerable people are, in fact, more affected. So what can we do? First of all, we need to fight climate change for sure, and the global emissions from our food systems are around 30% of the total anthropogenic greenhouse gas emissions. So we need to deploy response options across the entire food system from production to consumption, including, as I said, the food losses and wastes, and supporting adaptation and mitigation. So we will explore a bit more the landscape of response options we can see, and it is a large mitigation potential there between 2 and 9 or 10 gigaton of CO2 per year. The uncertainties are high. There are more with, in fact, how much adoption we can get with those technologies. But before exploring these responses, let me say that the challenges with the land systems are huge because we have challenges in terms of climate change adaptation. In those graphs at the left, you will see some, is this a pointer? Well, oh sorry, wrong button, okay. Yeah, let me say that on the top graph at the left, in purple, in highlighted colors, you have the risks linked with climate change adaptation, so the impacts of climate change. And the risks are, in those areas, higher because the seasonal cycle is disturbed by climate change. Then you have desertification, land degradation risks. You can see they are highlighted on the maps, mostly in tropical areas. Then you have also the food security issue, where we have countries with chronic undernourishment, the biodiversity hotspots, which are threatened, and then at the bottom you can see those areas where we have water over-abstraction and also where we have excessive nutrient flows by nitrogen and phosphorus. So if you want to add those challenges that are overlapping, you get to this map where you see that there may be 4 or 5 challenges, especially in the tropical countries, at the same time in the same region. It is interesting to note that the smaller the Human Development Index, the larger the number of land-based challenges per country. So it is really in countries that are already experiencing problems with health, problems with education, problems with GDP, that you have the largest number of challenges. So this also shows the conundrum and the problems we have with that nexus. So we've been exploring this IPCC report, special report of IPCC on climate change and land, the response options in a systematic way, so I cannot explain all of this, but you see they are organized in terms of agriculture, forests, other land uses or other ecosystems, and then in terms of the response options based on the value chain management, and response options based on risk management. Without entering into the details, the message here is that whenever you see a blue color, there are multiple benefits. So, in fact, if you take a single response like the increase in soil organic carbon, that response is always colored in blue. It has co-benefits for mitigation, adaptations, for desertification, land degradation, and food security. So we should, as an example, deploy that response on a large scale and urgently. But there are many other examples here. So we can do a lot, in fact. There are a few cases where you have negative implications, and this is often with food security, where, in fact, if you use more land, you may compete with the use for food, and that's a sort of trade-off between food and environment. So here again, without entering into all the details, you see how we can plot, we can map the responses in terms of their potential deployments. These are the land management responses, and when you see a color, this is a region where apparently there would be only co-benefits or no harm in deploying that response. And when the color is black, is that it is not adequate to deploy that response because we see adverse effects. So here again, in many regions, we could deploy a lot of responses with mostly co-benefits. However, you may see that the last map at the bottom and right, it is about bioenergy and what is called BECCS, as it is the bioenergy with capture of carbon and sequestration. There are few world areas where we could deploy this without harm, and the reason is that deploying this implies trade-offs with biodiversity and also with food security. So this is the graph I used during my pitch on the first day to see that, in fact, when we combine the responses we have in terms of agriculture, bioenergy, nature-based solutions, food access, and food sufficiency, we may still be able to reach the SDGs by 2050. But please consider we need to do a lot, and in only 25, 30 years, and it implies working in a coordinated way between the agriculture, between the environment sector, the climate policies, and also the food policies. So policy coordination internationally, but also within countries, is certainly something that needs to be highlighted. So now I'll move to discuss a bit more what are the innovation pathways and also what are the policies we can see in some countries. This is a graph we have at INRAE to explain how we want to shift towards carbon neutral and climate resilient food systems. You see that climate resilient, we can do quite a lot by having some breeding technologies used. This can be for plants, can be for animals. It is about breeding, phenotyping. Then we need to have soil and water conservation and to diversify the farms to mitigate the risks and have new value chains. For the carbon neutrality, it's obviously about abating the greenhouse gas emissions. It is also about soils and biomass carbon. It is also about bio-based inputs and supply chain efficiencies. So if we combine this, plus reduce the waste and losses, plus rebalance the diets, we get pretty close to carbon neutral and climate resilient food systems. And indeed, we are starting to see policies, for instance, in France about this, about transition towards agroecology, which is sort of driving targets that we have for the agricultural policy, about climate resilience with adaptation plans, with plans about water resources, and also about carbon neutrality. We have indeed a carbon neutrality strategy in France by 2050, and each year we have some carbon budgets that are established and should actually be according to the national strategy. So we also have reports. I'm in the French National Climate Change Committee. We are an independent committee reporting on how we are achieving those targets. It is therefore important that in that transition we have strong interdisciplinary research programs. That's an example of a research program we have at INRAE about climate change. And we said that it would be most important to understand how to combine in our sector with agriculture, forest, food, adaptation and mitigation. And this is in fact understudied so far. You have a lot of literature about climate change adaptation, a lot of literature about climate change mitigation, but you will not find much crossing those two dimensions. So there are really scientific frontiers in understanding how we can combine those, and we need to prioritize also this systemic transformation approaches and move towards transdisciplinarity involving the stakeholders. To explain why we need to do this is just one example, and I did not plot the most recent year, which is 2022, but that's the example of 2017, where we had a 30% decline in wheat yield in France, 20% drop in cereal production. We had about the same last year during summer 2022, and it could be as in that slide, because in fact of excess rainfall in spring, with problems with local flooding and disease pressures from the fungi, but it could also be because of heat and drought in summer, as we experienced last summer, 2022, or in 2003. So we are really in a difficult position because we should adapt crops to both the heat and drought and to both the risk of heavy rainfall and flooding. So how are we going to do this? It's a bit unclear. So that's why we need to increase also farm resilience. Traditionally, the thinking has been, let's do it with precision agriculture and advanced breeding. And this is in fact, keeping a bit the same system and improving it. We call it incremental adaptation. However, as I said, it's quite difficult with breeding only to understand how you can have the best plant material for heat and drought and for heavy rainfall. So we have to think a bit possibly about something else. And that's when we think about systemic adaptation. That's about soil and water conservation. In France, we say it's about agroecology also, meaning that we want to use better the natural systems regulation and use less inputs to rebalance the systems. So certainly by improving your soils, by having integrated water management at catchment scale, conservation agriculture, crop livestock integration, perennial crops like in agroforestry, you can move towards more resilient systems. And there is also a big challenge about transformative adaptation, which is really rethinking what you're producing and also combining it with the changes in the food consumption with the healthy diets. So there you see we could have some grass-legume mixtures, we could have more of the fruit trees with agroforestry, some nuts and so on. We could have diversified landscapes which would reduce the pest and disease pressure, and that's really connected to the food system transformation. However, it is not really supported strongly by the current policies. So that's just an example on how you're going to mix the crops with crop mixtures, with the grain legumes introduced, and this shows we have, in fact, many examples ongoing. With livestock, it's about breeding the robust and resilient animals and improving the welfare for the animals, closing the nutrient cycles, providing the livestock sector with more services, matching the societal expectations, and we can do quite a lot, for instance, by having adaptation of the breeds to heat, and this thermotolerance will be very helpful in the future. So these are examples of plant breeding for heat and drought in France that run from genomics to phenotyping. And we have advanced phenotyping facilities, which are both indoors and outdoors, with possibility to combine with actually the rain shelters and high CO2. These are examples about using, oh sorry, that's moving too quick, using the plant and animal diversity. So certainly the way we can conserve the biological resources is essential. We have a large national infrastructure about biological resources for plants, animals, but also for microbes. And there are European projects that are testing innovations in plant varieties. So it is important we not only rely on the modern pools used for crops, but we also rely on a much broader pool of genetic resources to face climate change. That's another example on how we can develop more environmentally friendly vineyards. You know, that's important for us in France. So we have to consider how to use biocontrol, genetic resistances. We have introduced some genetic resistance in some of those vines, and now we use 80 to 90% less of the fungicides, so it's really impressive what you can do. You can also work with the plant management in terms of architecture, of microclimate, and that's also converging towards climate change adaptation. Another example on what you could do with the plant-microbe interactions. So root phenotyping is something important for the future, and my slides are moving too fast. And here is, I will just move back. You see, we can address this, and actually you can have progress with this on the development of nitrogen fixation, and this is quite important for developing more green legumes and more pasture legumes to reduce the inorganic nitrogen fertilizer inputs. So that's one aspect, but if we go back to, let's say, how we can, in a low-carbon agriculture, manage the carbon pools and the greenhouse gas fluxes at the farm level, that's a slide which is possibly well known to some of you, showing the diverse sources of greenhouse gases in a farm. So I said you could reduce with legumes the nitrous oxide. You could certainly reduce the losses of fertilizers like ammonia volatilization. But when we did a study, this is a national scale study for French agriculture by 2030, we see there are a number of options we could deploy. And it's interesting, on this graph, you see the options like saving energy, increasing grazing, using and fixing legumes, or reducing the fertilizers. Well, it's interesting to note that the first part of this graph, according to expert calculations, comes at a negative cost. So mitigating by saving inputs and reducing production costs is clearly an option. Then you have other options that you can deploy that have a moderate cost. This could be also with reduced tillage, conservation agriculture. We are subsidizing biogas, so it is with a relatively moderate cost. And some options come with a higher cost. This is about cover crops, agroforestry, and so on. The potential is quite high. With those options, we were estimating we could abate about 30% of the global greenhouse gas emissions without changing the way we produce, without changing the mix of crops and livestock. I would like to focus now on storing organic carbon in soils because this has a huge potential. How can we do this? We can do it by greening the soils, if one can say. So having a continuous cover by vegetation, introducing cover crops, introducing grass leaves, for example, is very effective. And in this way, you can also protect soils against erosion and degradation. This requires, however, some assessment. We could assess that we can store 30 million tons of CO2 equivalent per year, which is really high for France, especially through those three practices: cover crops, grass leaves, increased organic fertilization. And we see that the potential is higher when you start from a depleted soil. That's where you can regain most carbon. And the costs are actually compatible with what can be done now. Around median cost was around 55 tons per ton of CO2, 55 euros per ton of CO2 in 2020. The big challenge we have now, and it is undertaken also by the European Commission, is to create a methodology for monitoring, reporting, and verifying the soil organic carbon change. We need to deploy that methodology if we want the private sector to pay carbon credits to farmers based on results. So that's a paper we had where we could show how to combine, in fact, the different data sets, the long-term experiments at benchmark sites, the flux data we have with flux towers, eddy covariance, with shorter experiments, the remote sensing, which is very important to verify the data, the activity data, and then the modeling, which is driven by inputs about climate, soils, land cover, but also by the farm activity data. So when you combine this, you can readily calculate the soil organic carbon change over time, and this sort of combination is really discussed to see what would be the framework in Europe and internationally to have a standardized MRV. It is interesting to note the progress we have with remote sensing, with the Sentinel satellites that have a 10-meter spatial resolution and a weekly update. We can actually show what are the crops, where are they, what is the vegetation cover, therefore what is the amount of carbon returning to the soil, and from this, with the farm data, we can calculate from the field to the country scale the soil organic carbon stock change. So this is really going to be, I think, deployed on a large scale. We also have some, let's say, integrative projects. This is one Horizon 2020 project, which is looking into how could you get carbon neutral farms. Well, you could get there with a number of actually practices combined, but certainly with efforts like living labs, where you accelerate innovation by having an innovation which is co-designed between the stakeholders, the farmers, the value chain, and the researchers. So this is the intention here. It is gradually deploying over a number of countries in Europe and over a number of contrasted farming systems and value chains. So let me stop here with my take-home messages. We do have a solution space for land and food transition. It is narrow and it requires coordinated research and innovation across 3 dimensions. Having resilient and low-carbon agriculture within a circular bioeconomy, having nature-based solutions and agroecology, which is a form of nature-based solution that certainly include soil health, forests, wetlands, peatlands, and having improved food access in the low-income countries, and healthy diets and food sufficiency. Food sufficiency meaning you don't need to consume too much, you just need what is needed for your health, and this leads to also rebalancing the diets. So there are many technical options that are available, but they are often not used because of past dependencies. Transitions need to be better coordinated, and that's one of the main reasons they are not deployed. It is because if you want to have transition both in agriculture, food, and the environment, it needs to be coordinated. This requires a way we rethink our priorities, and certainly health, climate change needs to be at the heart of those priorities, environment also, while supporting farmers and poor consumers. And this requires strong international commitments, strong policies, along with private sector engagement. Research and innovation need to be refocused with system thinking, inter- and transdisciplinarity. Living labs are a good example, support to public policies, independent assessments, while providing innovations to facilitate transitions. Thank you.